On the afternoon of June 3, 2026, the seafloor off southern Oregon slipped, and a magnitude 5.7 earthquake rolled out from a point about 95 miles west of a small coastal town called Pistol River. It was the strongest of 3 quakes felt along the west coast that same day. No one was hurt, no tsunami formed. Most people near the coast felt nothing at all, and a few dozen sent in reports of a gentle sway. If these calm reports help you wind down at night, you're welcome to subscribe and follow along. The cluster drew notice anyway, and not because those 3 quakes were dangerous. They sat on a fault that shakes often and rarely troubles land. What scientists are watching is timing and the much larger faults that lie nearby. New work on this coast suggests 2 of them may sometimes move within hours of each other, which would change the size of any future event. This report walks through what happened that afternoon, where it sat on the map, and why timing is the part worth understanding. The afternoon of June 3, 2026 was an ordinary one along the southern Oregon coast. The tide was working its way in. Boats sat in the small harbours. A little before 3 o'clock, the ground under the sea shifted, about 95 miles west of a town called Pistol River, and a magnitude 5.7 earthquake spread out from that spot. Magnitude is just a measure of how much energy the quake released. A 5.7 is a solid, moderate jolt, the kind that rattles dishes if you're close and fades to a soft roll if you're far. This one happened far out, under deep water. By the time the motion reached land, it had thinned to a gentle sway that most people never noticed. The United States Geological Survey, the federal agency that tracks earthquakes, logged it within minutes. The National Tsunami Warning Center checked the numbers and said there was no tsunami threat. No buildings cracked. No one was hurt. By the standards of a coastline that sits on some of the most active geology in the country, it was a quiet day. And yet this small quake is worth sitting with, because of where it sat and what stands near it. The ocean floor off the Pacific Northwest is not one simple thing. It is a patchwork of faults, each with its own habits, some loud and harmless, some silent and capable of far more. The quake on June 3rd belonged to the loud and harmless kind. The faults that worry scientists were close by, but they did not move that day. To understand why a forgettable jolt drew a second look, it helps to start with the plain facts and build outward. The quake struck at a depth of about 6.5 miles below the seafloor. In earthquake terms, that counts as shallow. Shallow quakes tend to shake harder right above them, but this one was so far offshore that the hard shaking spent itself over open water before it ever reached a person. Roughly 37 people sent in reports of feeling it, mostly a brief mild motion along the coast. The strength of a quake and the way it feels are 2 different things, and the gap between them matters here. A 5.7 sounds serious, and up close it would be. Distance softened it. The same quake under a city would have made the news for very different reasons. Out at sea, it became a line in a database, and a few dozen felt reports. The location is the first clue to the whole story. Pistol River is a small place near the Oregon and California border, where the coast turns rugged and the towns are few. The quake was not under the town. It was far out past the surf, in a part of the seafloor where several pieces of the Earth's crust meet and grind. That meeting place has a name, and it is not the famous one people fear. It is a quieter neighbour, and knowing the difference is the key to reading this event calmly. Earthquakes in this region almost always get filed in people's minds under one heading. The Pacific Northwest carries the memory of a giant fault offshore, the one capable of a true disaster. So when the ground moves anywhere near Oregon, the first thought reaches for that giant. Most of the time, that first thought is wrong. The June 3rd quake is a clean example. It came from a different fault, with a different motion, carrying a different level of risk. That is why the careful work of placing a quake matters so much. A single number, a magnitude, tells you very little on its own. Where the quake happened, how deep it was, and which fault it sat on together tell you whether to shrug or to pay attention. On June 3rd, all 3 pointed toward shrug, and the agencies said as much plainly and quickly. Still, the day was not finished. The Oregon quake was not alone. 2 more shakes were felt elsewhere along the west coast in the same stretch of hours, and that small grouping is what turned a single jolt into something people called a cluster. A cluster invites questions that one quake does not. People wanted to know if the three were connected, and whether a run of quakes in one day meant something larger was building. Those are fair questions, and they have honest answers. The place to begin is with what a cluster actually is, and why 3 quakes in a day is more common and more ordinary than it first sounds. 3 earthquakes along one coastline in a single day feels like a pattern. The mind reaches for a thread that ties them together. Often, there is no thread at all. The Earth's crust is busy everywhere all the time, and the West Coast is one of its busiest stages. On a typical day, the ground shifts somewhere along that coast more than once, usually too faintly to feel. Group of few felt quakes into the same afternoon, and it looks like an event, even when it is just the normal background turned up a notch. Scientists have a careful word for a true run of quakes in one area. They call it a swarm. A swarm is a set of small to moderate quakes in the same patch of ground over some stretch of time, and the thing that sets it apart is its shape. In an ordinary sequence, one big quake comes first, the main shock, and smaller aftershocks follow as the fault settles. In a swarm, there is no clear leader. The quakes come in a looser bunch, and the strongest one might land in the middle rather than at the start. The June 3rd quakes did not even rise to that. They were spread along the coast rather than packed into one spot, and they sat on different parts of the seafloor. Calling them a cluster was a fair, loose description for 3 felt quakes in one day. It was not a sign that one fault was waking up and firing in a series. Spacing matters. Quakes that share a single fault and a single cause tend to sit close together and close in time. These did not. There is a useful comparison here, and it is worth one moment. Think of the whole West Coast as a long, old wooden floor. Step on it anywhere and it creaks. Most creaks mean nothing. They are the house settling, the way it always has. A cluster of creaks in one evening does not mean the floor is about to give way. It means you happen to walk across several boards in a row. The crust behaves a little like that, with countless small adjustments that rarely add up to anything. What makes people nervous is the leap from many small quakes to one giant quake. The fear runs like this. If the ground keeps shaking, maybe it is building toward the big one. The science does not support that leap, at least not in any way that lets anyone predict it. Small quakes happen constantly, and the overwhelming majority lead nowhere. They are not reliable warnings. The United States Geological Survey is blunt about this. No one can predict the exact time or place of any earthquake. A cluster does not change that, and it does not raise the odds in a way anyone can act on. This matters for staying calm and staying honest at the same time. It would be easy to take 3 quakes and spin them into a countdown. The facts do not allow it. 2 of the 3 June 3rd quakes were minor and scattered. The third, the 5.7 off Oregon, was the only one strong enough to draw real notice, and even it did no harm. So the cluster, on its own, was a non-event. The reason it still earned a closer look is not the cluster itself. It is the address. These quakes happened in a stretch of ocean that sits beside the most closely watched fault in North America, and within reach of a question that scientists have been chewing on for years. The quakes were small. The neighborhood was not. To see why the neighborhood matters, the next step is to put the June 3rd quake exactly on the map. Not the rough idea of off Oregon, but the precise piece of seafloor it came from, and the boundary lines running through that water. Once the map is clear, the difference between a harmless jolt and a genuine threat becomes easy to see, because out there, only a short distance apart, the two live side by side. Picture the Pacific seafloor off Oregon as a place where 3 great slabs of the Earth's crust come together. These slabs are called tectonic plates. They are the rigid pieces that make up the outer shell of the planet, and they move slowly and steadily, carried by heat deep below. Where 2 plates meet, you get a fault, a boundary where the rock is under strain. Off the Pacific Northwest, the boundaries are not simple lines. They cross and branch, and each branch behaves in its own way. The June 3rd quake came from a branch called the Blanco Fracture Zone. It runs through the ocean roughly west and a little south of the Oregon coast, well out past the shallows. Along this zone, 2 plates slide past each other sideways, scraping rather than colliding. That sideways grind is the source of the frequent moderate quakes the zone produces. The Blanco Fracture Zone is one of the most active stretches of seafloor on the west coast, and most of what it does never reaches a person on land. A short distance to the east lies a very different boundary, and the contrast is the whole point. There, the plates do not slide past each other. One dives beneath the other. That diving boundary is the Cascadia Subduction Zone, the giant that the region fears. The Blanco Zone and Cascadia sit near each other in the same patch of ocean, yet they carry completely different levels of risk. One scrapes and shrugs, the other locks and waits. Knowing which boundary a quake came from tells you almost everything about whether to worry. On June 3rd, the strongest quake came from the Blanco Zone, the scraping kind. That single fact is why the agencies could say, within minutes, that there was no tsunami threat and no cause for alarm. The motion was the ordinary sideways grind of a fault that does this all the time. The Blanco Zone has a long record of these moderate quakes, and they rarely make news. In late October of 2024, a magnitude 6.0 struck out in the same general stretch of ocean, west of the Oregon town of Bandon. It too produced no tsunami and no damage. Quakes in the 5 and 6 range out there are simply part of how that piece of seafloor lives. They are loud in the instruments and quiet on the coast. This is the part that gets lost when a quake makes a headline. A magnitude 5.7, rid cold sounds like something to brace for. Tie it to the Blanco Zone and put it 95 miles out to sea, and it becomes what it was, a routine release of strain along a fault built to release it. The number did not change, the context did all the work. There is a reason the region cannot fully relax even so, and it is honest to name it. The faults out there are close together. A quake on the Blanco Zone does not, on its own, set off the larger boundary nearby. But the two are part of one busy system, and that closeness is exactly what scientists have started to study with fresh eyes. The June 3rd quake did not trigger anything. The question is whether, over the long span of history, motion on one part of this system has ever lined up with motion on another. That question comes later, and it is the heart of the story. For now, the map gives a clear and steadying picture. The quake sat on a scraping fault, far offshore, the kind that shakes often and threatens little. The fearsome boundary lay nearby but stayed still. The coast went about its day. To make that picture complete, it helps to understand why the kind of fault matters so much for the sea itself, because the way a fault moves decides whether the ocean stays flat or rises. That difference, between a sideways grind and a sudden lift of the seafloor, is what separates a quiet quake from a deadly wave. The thing most people fear from an offshore earthquake is not the shaking, it is the water. A tsunami can cross an ocean and arrive with terrible force, and the Pacific Northwest knows it lives in range of that risk. So the first question after any quake under the sea is a simple one. Will the water rise? On June 3rd, the answer was no, and the reason comes down to how the fault moved. A tsunami is born when the seafloor itself lifts or drops suddenly, shoving the whole column of water above it. Imagine pushing up sharply on the bottom of a full bathtub. The water has to go somewhere, so it bulges and spreads outward as a wave. That is, in plain terms, how a subduction zone builds a tsunami. When one plate lurches up over another, it heaves a vast slab of seafloor, and the ocean above it is forced to move. The Blanco fracture zone does not work that way. Its plates slide past each other sideways, more like two hands rubbing flat against each other than one hand shoving up under the other. Sideways motion does not lift the seafloor much. With little vertical shove, there is little to displace the water above, so even a solid quake on that zone like the 5.7 on June 3rd leaves the sea surface nearly undisturbed. The energy goes sideways through the rock, not upward into the water. This is why the National Tsunami Warning Center could clear the event so fast. The agency does not wait to see what the waves do. It reads the quake's location, depth, and type of motion, and it knows from long study which combinations can raise a wave and which cannot. A moderate sideways quake on a known fracture zone falls cleanly into the cannot column. The all clear was not a guess. It was a reading of the fault's nature. The contrast with the larger neighbour is stark, and it is worth holding clearly. If the same patch of ocean had moved on the subduction zone instead, with one plate heaving over the other at great magnitude, the story would be entirely different. That kind of quake can lift hundreds of miles of seafloor at once, and send a wall of water toward the coast within minutes. The Pacific Northwest plans for exactly that scenario, with evacuation routes painted on coastal roads and signs pointing uphill. None of that machinery was needed on June 3rd because the fault that moved cannot do that job. There is a useful rule of thumb buried in all this. Magnitude alone does not tell you about tsunami risk. A large sideways quake may raise no wave at all, while a more modest vertical quake in the wrong place can be dangerous. What matters is whether the seafloor lifted. The size of the quake sets the potential. The type of motion decides whether that potential turns into water on the move. For people who live along this coast, the practical lesson is steady and simple. Official warnings are built on this exact reasoning, and they are fast and reliable. When the sea is truly at risk, the alerts come quickly and tell people to move to high ground. When a quake like the June 3rd event strikes, the same system reads it and says, plainly, that the water will stay where it is. Trusting that system, and knowing the natural warning signs for the coast, is the calm and correct response. So the sea stayed flat because the fault that moved was a scraping one, not a heaving one. That single distinction did all the protective work. It is also a reminder of how much rides on the details of a fault, the kind of details that take careful instruments and trained eyes to pull from a few seconds of shaking. How those details get measured in the minutes after the ground moves is its own quiet feat, and it is what let the agencies speak with such confidence so soon after the seafloor slipped. When the seafloor moved on June 3rd, no one saw it. The slip happened miles under deep water, far from any witness, and yet within minutes, agencies could state the quake's size, its depth, its exact spot, and the kind of fault it came from. That speed is not luck. It rests on a web of instruments and a method worked out over more than a century, and it is worth understanding because it is what turns a vague tremor into hard, trustworthy facts. The core instrument is the seismometer. At its heart, it is a device that senses ground motion and records it as a wiggling line. Hundreds of them sit across the west coast, many run by the Pacific Northwest Seismic Network, a group based in the region that watches Oregon and Washington closely, alongside the federal United States Geological Survey. When a quake sends waves through the rock, each station feels them pass and writes down the exact moment they arrive. Locating the quake comes from those arrival times. Earthquake waves travel at known speeds, and they reach nearby stations before distant ones. By comparing when the shaking hits several stations, scientists can trace the waves backward to the single point they came from. With enough stations, the location tightens to within a few miles, even out under the ocean. It is the same idea as judging how far off a storm is by the gap between the lightning and the thunder, only run across many listening posts at once and solved with precision. Depth comes from the same timing, read more finely. A quake right under a station and a quake far below it send their waves on different paths, and those paths leave subtle marks in the records. From them, scientists worked out that the June 3rd quake sat about 6.5 miles down. That depth tells its own part of the story. Shallow quakes like this one carry their energy closer to the surface, which usually means stronger shaking nearby, though here the nearby was open sea. Magnitude, the famous number, comes from the size of the waves themselves. Bigger slip on the fault sends out bigger waves, and the instruments measure how big. The scale is built so that each step up means a large jump in energy, not a small one. A magnitude 6 releases far more energy than a magnitude 5, not just a little more. So the gap between the June 3rd 5.7 and the kind of quake the region truly fears, up in the magnitude 9 range, is not a short step. It is an enormous one, with the Great Quake releasing thousands of times more energy. The type of fault motion is read from the pattern of the waves as they spread in different directions. A sideways slip pushes the ground one way on one side and the other way across from it, and that signature shows up across the network. From it, scientists could tell that the June 3rd quake was the scraping, sideways kind, the Blanco fracture zone's usual motion, and not the heaving kind that lifts the sea. That single reading is what cleared the tsunami concern within minutes. All of this happens fast because much of it is automated. Computers crunch the first arrivals and post an early estimate within a minute or two, and then human analysts refine it as more data comes in. The first numbers can shift a little as the picture sharpens, which is why an early magnitude sometimes nudges up or down before settling. That is not error. It is the system tightening its aim as more stations report. The result is that a quake no one witnessed becomes a set of solid facts almost at once. Size, place, depth, fault type, tsunami risk, all of it pulled from the trembling of distant needles. It is a quiet kind of marvel, and it is what lets the public hear, calmly and quickly, that there is nothing to fear. Those instruments measure the quake. They do not measure how it felt to the people who were there, and that human side of the record comes from a very different source, one made of ordinary folks reporting a sway they noticed on a Wednesday afternoon. The instruments record what the rock did. They cannot record what a person felt standing in their kitchen when the floor moved. For that, the United States Geological Survey turns the public into part of the measurement. It runs a simple tool called Did You Feel It?, where anyone who noticed a quake can report it. After the June 3rd quake, about 37 people did, mostly along the southern Oregon coast, describing a brief and gentle motion. That number is small, and it tells a story of its own. A magnitude 5.7 is a meaningful quake, yet only a few dozen people felt it enough to report. The reason is distance. The quake struck 95 miles out to sea, and shaking weakens fast as it travels. By the time the waves reached the coast, they had spread thin and soft. What arrived was a slow sway, not a sharp jolt, the kind of thing a person might blame on a passing truck if they noticed it at all. This points to a distinction that matters whenever a quake is in the news. Magnitude and intensity are not the same thing. Magnitude is the quake's size at its source, a single fixed number for the whole event. Intensity is how strongly the ground shook at a particular spot, and it changes from place to place. Right above the June 3rd quake, the intensity was high, but that was over empty ocean. On land, 95 miles away, the intensity was low. Same quake. Very different experience depending on where you stood. Scientists put numbers on intensity using a scale that runs from barely noticed to total destruction. The low end is a faint motion that only a few people sense, often those sitting still on an upper floor. The high end is the kind of violent shaking that throws furniture and cracks buildings. The June 3rd quake landed at the gentle end on the coast, a light sway felt by some and missed by most. That is exactly what you expect from a moderate quake far offshore. The felt reports do real work beyond simple curiosity. When people across a region log what they felt, the pattern of those reports helps confirm the quake's location and shows how the shaking spread across different ground. Soft soil shakes more than solid rock, so the same quake can rattle one neighbourhood and barely touch the next. The crowd of reports paints a map of that variation, a map no single instrument could draw on its own. For the June 3rd quake, the map was thin and quiet, which matched everything else about the event. No reports of damage came in. No one described things falling or cracking. The strongest accounts were of a noticeable sway, enough to make someone pause and wonder, not enough to send anyone for cover. It was, in human terms, a curiosity rather than a scare. It is worth pausing on how reassuring that thinness is. A quake that produced only a few dozen mild reports with no damage is a quake that did its business safely out at sea and sent only a whisper to shore. If the same magnitude had struck close to a coastal town or under a city inland, the reports would have numbered in the thousands and told a harder story. The gentle record from June 3rd is itself a kind of confirmation that the event was minor where it counted, on land, where people live. This human layer rounds out the picture of the quake itself. The instruments gave the hard facts, the felt reports gave the lived experience, and both pointed the same calm direction. A moderate sideways quake, far out to sea, that shook the coast softly and harmed nothing. That should be the end of the matter, and for the quake on its own it is. But the story did not end there, and the reason has nothing to do with how June 3rd felt. It has to do with a name that hangs over this entire coastline, a fault so large and so feared that every quake near Oregon gets measured, in the public mind, against it. To understand why a harmless jolt kept people talking, you have to understand that name, and why it sits so heavily on the Pacific Northwest. There is a reason a minor quake off Oregon makes people uneasy when the same quake off another coast might pass without notice. The Pacific Northwest lives in the shadow of a single enormous fault, and its name colours how the region hears every tremor. That fault is the Cascadia Subduction Zone, and the fear attached to it is not hype. It is grounded in hard science and in a real event that left its mark across the Pacific. The unease works like a reflex. The ground moves somewhere near Oregon or Washington, and the first thought for many jumps straight to Cascadia. Is this it? Is this the start of the big one? On June 3rd, the honest answer was no, and the agencies said so clearly. But the reflex is understandable, because the region has spent decades learning just how much that fault could do, and the lesson has sunk deep. Part of what feeds the unease is geography. Cascadia and the smaller faults around it share the same patch of ocean. The Blanco Fracture Zone, which produced the June 3rd quake, lies in the same offshore neighbourhood as the Great Subduction Zone. To someone watching a map of quake dots appear off the coast, the dots from a harmless fault and the dots from the fearsome one land close together. The eye does not separate them. The mind files them all under the same worry. This is why the careful work of telling the faults apart matters so much for public calm. A quake on the Blanco Zone and a quake on Cascadia might appear only a short distance apart on a map, yet they mean entirely different things. One is the routine grind of a scraping fault. The other would be the opening of a disaster the region has braced for across a generation. Reading the difference quickly and plainly is what keeps a small quake from becoming a large panic. The fear also has a particular texture because of timing in a larger sense. The Pacific Northwest has been told, accurately, that it is within the window when a great Cascadia quake could happen. That knowledge sits in the background of daily life, in school drills and emergency kits and signs along the coast. When the ground moves, that background knowledge surges forward. A small quake becomes a reminder of the large one waiting, even when the two have nothing to do with each other. It helps to be honest about what that waiting actually means, because the word overdue gets thrown around in ways that mislead. The fault does not run on a schedule like a train. It releases on its own slow, uneven rhythm, and being within the window is not the same as being late for an appointment. The June 3rd quake did not move Cascadia closer to rupture, and it did not push it back. The two are separate stories that happen to share a coastline. Still, the reflex is not foolish. It comes from a region taking a real threat seriously, which is a healthy thing. The danger is only when the reflex turns a harmless event into a false alarm, or when repeated false alarms wear people down until they stop listening. The calm path runs between those errors. Take Cascadia seriously as the long-term threat it is, and read each individual quake on its own merits. June 3rd, read on its merits, was nothing. Cascadia, read on its own, is everything. So the name that hangs over the coast is worth understanding in full, not as a vague dread, but as a real and well-studied fault with real and well-studied limits. To do that, the next step is to look at Cascadia plainly. What it is, how it works, why one plate diving beneath another can store the energy for a quake thousands of times stronger than the one felt on June 3rd, and what that stored energy would mean if it ever let go. The Cascadia Subduction Zone is a boundary in the ocean where one piece of the Earth's crust is slowly diving beneath another. To the west sits a plate called the Juan de Fuca, a relatively small slab of seafloor. To the east sits the much larger North American plate, the one that carries the coast and everything on it. Along a line that runs roughly 1,000 miles, from Northern California up to British Columbia, the Juan de Fuca plate is being forced down and under the edge of North America. This diving is what the word subduction means. One plate goes under another and sinks into the hot interior of the Earth. It happens slowly, on the order of an inch or two a year, about the pace your fingernails grow. You would never see it move. Over thousands of years, though, that steady push adds up to enormous strain, and the way that strain releases is what makes a subduction zone so dangerous. The trouble is that the two plates do not slide past each other smoothly. They stick. Along much of Cascadia, the diving plate and the overriding plate are locked together, jammed by friction. The deep, slow push from below keeps coming, but the locked edge does not budge. So the rock bends and stores the energy. Like a stick, you bend further and further without it snapping. The coast itself is slowly squeezed and lifted as this happens, by amounts too small to feel but real enough to measure. At some point, the friction gives. The locked edge breaks free all at once, and the bent rock springs back in a single violent lurch. The overriding plate heaves up and seaward, the stored energy of centuries unleashed in a few minutes of shaking. Because the locked zone can stretch for hundreds of miles, the whole length can let go together, which is what makes a subduction quake so large. This is the kind of event that reaches the magnitude 9 range, the size that releases thousands of times the energy of the June 3rd quake. And because that heave lifts a vast slab of seafloor, it shoves the ocean above it and sends a tsunami racing toward the coast. For the Pacific Northwest, the wave would arrive fast, in some places within 15 to 20 minutes, too soon to wait for an official alert. This is why coastal communities are taught to treat the shaking itself as the warning. If the ground rolls long and hard near the coast, the instruction is to move to high ground without waiting to be told. The shaking from such a quake would be unlike the brief sway of June 3rd in every way. A great Cascadia quake would shake for several minutes, not several seconds. Long shaking does more damage than short shaking because it gives weak structures time to fail and loose soils time to lose their strength. The contrast with the gentle June 3rd event could not be sharper. One is the routine breath of a scraping fault. The other would be the once-in-centuries release of a locked giant. It is important to hold both truths at once. Cascadia is a genuine and serious threat, capable of one of the largest disasters the country could face. And the June 3rd quake had nothing to do with it. The small quake came from a different fault, with a different motion, carrying a different risk. The giant stayed locked and quiet, doing what it has done for more than 3 centuries, which is to wait. How long it has waited, and what that waiting tells us, is the next piece. The most powerful evidence for what Cascadia can do does not come from a modern instrument at all. It comes from a single night more than 300 years ago, recorded not by scientists but by the ocean, by drowned forests on the Oregon coast, and by careful clerks across the Pacific in Japan, who wrote down a wave that arrived with no earthquake to explain it. The clearest proof of what Cascadia can do comes from the night of January 26th, in the year 1700. On that night, the locked fault gave way along much of its length, and a great earthquake struck the Pacific Northwest. No European settlers were present to write it down, and the native peoples who lived through it passed the memory through their own histories. For a long time, the size and timing of the event were a puzzle. The way scientists finally solved that puzzle is one of the best detective stories in Earth science. The first clue was in the trees. Along several Pacific Northwest estuaries stand what are called ghost forests, groves of dead cedar trunks still rooted in tidal mud. These trees once grew on dry coastal land. They died when that land suddenly dropped during a great quake, and the sea rushed in over their roots, drowning them in salt water. By studying the growth rings in the dead wood, scientists could tell that the trees all died at the same time, in the same season, pointing to one sudden shared event. The rings narrowed the timing to around the year 1700, but they could not pin the exact date. The final answer came from across the ocean. In Japan, along the Pacific coast, village and town records from that era describe a tsunami that struck without warning. There had been no felt earthquake to explain it, so Japanese writers later called it an orphan tsunami, a wave with no local parent. The records were careful enough to fix the date and even the hour the wave arrived. Scientists worked backward from that arrival. A tsunami crosses the Pacific at a known speed, so the time the wave reached Japan tells you when it must have started on the far side. Run the clock back across the ocean, and the answer lands on the evening of January 26, 1700 on the coast of the Pacific Northwest. The drowned forests, the Japanese records, and the travel time of the wave all agreed. A single great Cascadia earthquake, large enough to send a tsunami all the way to Japan, had struck that night. The size of the wave in Japan pointed to the size of the quake that made it. To shove enough water to cross the entire Pacific and still arrive as a damaging wave, the seafloor off the northwest had to have heaved on a massive scale. That fits a rupture along much of Cascadia's length at once, the full 1,000-mile zone or a large part of it, reaching into the magnitude 9 range. This was not a guess pulled from fear. It was a number built from drowned trees and old ledges, checked against the physics of waves. The native histories of the region carry the same event, told in their own terms. Stories along the coast describe the ground shaking and the ocean rising, of whole villages lost to the water in a single night. For generations these were oral accounts, and when scientists pieced together the geological record, the two kinds of knowledge lined up. The people who lived on that coast had been telling the truth about the night the land dropped and the sea came in. What makes 1700 so powerful is that it turns Cascadia from a theory into a fact with a date. The fault is not merely capable of a great quake in the abstract. It produced one on a known night, with effects recorded on two sides of the Pacific. That is the event the Pacific Northwest braces for, because it is the event the region has already lived through once. 1700 also starts a clock that still runs today. If that was the last great rupture, then the strain has been building ever since for more than 3 centuries. How long these quakes typically wait between events, and what the current gap does and does not tell us, is the next question, and it is where a lot of loose talk about being overdue needs to be replaced with what the evidence actually supports. If the last great Cascadia quake struck in 1700, the natural question is how long the fault usually waits between such events. Scientists have an answer, drawn from the same kind of detective work that pinned down that night. They have read the record of past quakes written in the seafloor and in coastal mud, and that record stretches back thousands of years. From it comes a rhythm, though a loose and uneven one. The way they read it is clever. When a great quake shakes the continental margin, it triggers underwater landslides that send sediment sliding down into the deep sea, where it settles into a distinct layer. Each great quake leaves its own layer. By drilling cores into the seafloor and counting these layers down through time, scientists can tell how many great Cascadia quakes have happened and roughly how far apart they fell. The deeper the layer, the older the quake. That record shows great Cascadia quakes coming, on average, somewhere in the range of every 200 to 600 years. The spacing is not regular. Some gaps were shorter, some much longer. The fault does not fire on a fixed schedule. It releases when the strain finally overcomes the friction holding it, and that moment varies from one cycle to the next. So the average is a guide, not a timetable. Now lay the clock against today. The last great quake was in 1700, which means more than 326 years have passed. That gap sits inside the typical range, on the longer side of it, but not beyond it. In plain terms, the Pacific Northwest is within the window when the next great quake could come. It could happen in your lifetime. It could also hold off for another century or more. Both are consistent with the record. This is where the word overdue does real harm, and it is worth correcting plainly. Overdue suggests a payment that was due on a date and has been missed, as if the fault owes a quake and is running late. The fault owes nothing and keeps no calendar. Being within the window means the odds are meaningful and worth preparing for, not that a quake is imminent or that each passing year makes one dramatically more likely. The strain builds steadily, but the release is not a scheduled appointment. The June 3rd quake fits nowhere in this clock, and that is the point worth holding. It came from the Blanco zone, a different fault entirely, and it released a tiny fraction of the energy a great Cascadia quake would. A moderate quake on a neighbouring fault does not load Cascadia, does not unload it, and does not move the long clock forward or back in any measurable way. The two run on separate tracks. The cluster was noise. The clock keeps its own slow time regardless. There is comfort and seriousness woven together here, and both are honest. The comfort is that no single small quake, and no cluster of them, signals that the great one is about to strike. There is no countdown ticking in those felt reports. The seriousness is that the great one remains a real possibility within a span that matters for people alive now, which is why preparation is wise even on a quiet coast on a quiet day. Knowing the rhythm is one thing, putting an actual probability on it is another, and the agencies that study Cascadia have done exactly that. They have turned the long record and the current gap into numbers, percentages that describe the chance of a great quake in the decades ahead. Those numbers are sober, specific, and sometimes misunderstood, and looking at them honestly is the clearest way to size the real threat without tipping into either denial or dread. Scientists have done the work of turning Cascadia's long record into actual odds, and the numbers are worth stating plainly, because they are often stretched in one direction or the other. In its 2025 hazard update for the Pacific Northwest, the United States Geological Survey estimated roughly a 30% chance of a magnitude 8 or greater quake in the southern part of Cascadia within the next 50 years. That is a real and serious probability, neither tiny nor a near certainty. A separate way of looking at it focuses on the full rupture, the whole zone letting go at once in a magnitude 9 event. The Pacific Northwest Seismic Network puts the chance of that full margin rupture lower. in the range of 10 to 15% over the next 50 years. The difference between the two numbers is not a contradiction. It reflects an important fact about how Cascadia can break, which is that it does not have to break all at once. That fact deserves a plain handle. A full margin rupture is the whole 1,000-mile zone breaking together, the magnitude 9 scenario, the 1700 event. A partial margin rupture is a shorter section breaking on its own, which still produces a very large quake, perhaps a magnitude 8, with serious shaking and tsunami danger along part of the coast, but not the entire catastrophe. Partial ruptures appear to happen more often than full ones, so the chance of some great quake is higher than the chance of the single largest possible one. Other studies have framed the odds in their own terms, and the range is honest to acknowledge. One analysis published in a major scientific journal put the chance of a Cascadia rupture at around 15% in the next 50 years, rising to nearly 30% by the year 2100. Different methods and different definitions yield somewhat different figures. What they share is the same broad message. The threat is real and significant over the span of decades, and it is not an imminent certainty. Numbers like these can be read two opposite and equally wrong ways. One reading hears 30% and panics, treating a great quake as if it were about to happen any moment. The other hears the same 30%, notices that means a 70% chance it does not happen in 50 years, and shrugs the whole thing off. The honest reading sits between them. A roughly 1 in 3 chance over 50 years is high enough to take seriously and prepare for, and low enough that daily life need not be ruled by dread. It matters too that none of these odds say anything about a particular day or year. They describe the chance across a long span, not a prediction of when. The United States Geological Survey is consistent and blunt on this point. No one can predict the exact time or place of any earthquake. The probabilities are a long-range forecast for planning, the way you might know a region's flood risk over decades without knowing which storm will be the one. And here is where the June 3rd quake finally settles into its proper small place. That moderate jolt on the Blanco zone did not change a single one of these numbers. It did not raise the 30% or the 10 to 15% by any amount anyone can measure. The odds for Cascadia rest on the slow loading of the subduction zone over centuries, not on what a neighbouring fault does on a Wednesday afternoon. The cluster and the long-term forecast are simply unrelated. So the picture, after 12 steps, is clear and calm. A small, harmless quake struck a scraping fault far off Oregon. The fearsome fault nearby stayed locked, carrying a real but long-range threat measured in sober percentages. If that were the whole story, the June 3rd quake would deserve no second thought at all. But there is a reason it kept scientists talking, and it is not the cluster, and it is not the standard Cascadia forecast either. It is a newer and stranger question, one about timing, and about whether the great faults of this coast have ever moved not alone, but together. The new attention to this coast does not come from how large a future quake might be. It comes from when it might strike, and beside what. The cluster that afternoon was a small thing, but it landed during a season when scientists were already rethinking the timing of West Coast quakes in a serious way. The old picture treated the Great Fault as a lone giant. One day it would slip, produce a magnitude 9, and that would be the disaster the region planned for. Big, terrible, but single. A new line of research suggests that picture may be incomplete, and that the truly hard case is not one giant quake, but two, close together in time. The idea is that the Great Subduction Fault off the Pacific Northwest and another famous fault to the south may sometimes move in concert. The Southern Fault is the one that runs through California, the long crack that has shaped that state's history of earthquakes. For decades, these two were studied as separate systems with separate clocks. The fresh work asks whether their clocks are linked. The lead voice on this is a marine geologist at a university in Oregon, who has spent much of his career reading the record of past quakes off this coast. In a study published recently, he and his colleagues laid out evidence that the two faults have, at times, ruptured within a very short span of each other. Not centuries apart, within minutes to hours. His own way of putting it is striking in its calm. The Great Fault, he has said, has long been treated as the worst case the region could face. His work suggests it may not be the worst case at all. The worst case may be the two faults going off together. That is the thread the cluster brushed against. 3 small quakes in one day mean nothing on their own for this question. But they arrived while the science of West Coast timing was shifting under everyone's feet, which is why a quiet afternoon drew more notice than its size deserved. To follow the new idea, the map has to shift south to a single stretch of California coastline where the two great faults very nearly touch. That meeting place is the key to the whole question, and it is where the next chapter goes. The place at the center of this story is Cape Mendocino, on the northern California coast. It is a rugged, lightly populated stretch of shoreline, and beneath the water just offshore, three of the most important faults in North America come together. This meeting point has a name. Scientists call it a triple junction, the spot where three boundaries between crustal plates intersect. At Cape Mendocino, the Great Diving Fault from the north, the Long Sliding Fault from the south, and a third boundary out to sea all converge in one crowded patch of seabed. Few places on Earth pack so much tectonic machinery into so small an area. That crowding is exactly why the region matters. North of the junction lies the subduction zone, where one plate dives beneath another. South of it lies the California Fault, where two plates grind sideways past each other. The junction is the hinge between these two very different systems. Whatever connection the two faults might share, this is where their stories would meet. It is also one of the busiest earthquake areas on the West Coast. The grinding of three boundaries against one another produces frequent quakes, large and small, year after year. People in the nearby towns are used to the ground moving. For scientists, the steady activity makes the junction a natural laboratory, a place where the behavior of both great faults can be watched at close range. The geography does something useful for the research too. Because the two faults nearly touch here, the sediment on the seafloor near the junction can record shaking from either one. A great quake on the northern fault and a great quake on the southern fault would both leave their marks in the same patch of mud. That overlap is what makes it possible to compare their timing at all. This is the reason the investigation centered on Cape Mendocino rather than anywhere else. To ask whether two faults move together, a scientist needs a place where both faults write into the same page. The junction is that page. The layers of sediment just offshore hold a mingled record of quakes from north and south, stacked through thousands of years. Reading that record was the task, and the first crucial piece of it came almost by accident, on a research voyage that drifted off course more than 2 decades ago. What the crew found when they wandered into the wrong patch of ocean set this entire line of work in motion. The next chapter tells how it happened. The discovery that opened this question began with a mistake. In the year 1999, a research ship was working off the coast, collecting cores of mud from the seafloor near the Great Northern Fault. A core is a long tube of sediment, pushed down into the seabed and pulled back up with the layers intact, a slender column of the ocean floor's history. While gathering these cores, the team drifted off their planned position. The ship ended up about 55 miles south of Cape Mendocino, well past the junction, and into territory shaped by the California Fault rather than the northern one. It was the wrong spot for their original purpose, the kind of error that usually means simply moving back on station. Instead of abandoning the location, the researchers decided to take a core there anyway. Since the ship was already in place, they reasoned they might as well sample the seabed and see what it held. It was an offhand choice, the scientific equivalent of looking inside a drawer you opened by accident. That choice turned out to matter a great deal. When they examined the core from the off-course position, the layers inside did not look like the ones they were used to. Something about the sequence was reversed, arranged in a way that did not fit the normal pattern of seafloor mud. The crew had stumbled onto a record that hinted at an unusual kind of event, one that joined the two faults rather than separating them. At the time, the meaning was not clear. The strange core went into the archive, a curiosity logged and set aside. But it planted a question in the lead scientist's mind that would not leave, a question about whether the northern fault and the southern fault might be connected in their timing. Decades of further work grew from that single accidental sample. This is how a fair amount of science actually moves. Not always by a planned march toward an answer, but sometimes by a wrong turn that puts a careful observer in front of something unexpected. The team was prepared to notice that the core was odd, and prepared to wonder why, and that readiness turned a navigation error into the seed of a discovery. To understand what made that core so telling, and why a reverse set of layers could point to 2 earthquakes instead of 1, The next chapter looks closely at how the seafloor records a quake in the first place. The mud, it turns out, keeps a careful diary. The seafloor keeps a record of earthquakes written in mud. Understanding how it does this is the key to everything the core's revealed, and the idea is simpler than it sounds. When a great quake shakes the edge of a continent, the violent motion can dislodge loose sediment piled up on the underwater slopes. That sediment breaks free and slides downhill in a vast underwater avalanche, a churning cloud of mud and sand racing into the deeper basins offshore. When the avalanche finally slows and settles, it leaves a distinct layer of material on the seafloor. Scientists call these layers turbidites. Each one marks a moment when something shook the slopes hard enough to start an avalanche, and the most common trigger for a large one is a major earthquake. So a turbidite is, in effect, a fingerprint left behind by a great quake, pressed into the floor of the ocean. The layers stack in order, oldest at the bottom and youngest at the top, like pages in a book that is never reshuffled. Drill a core down through them, and you read the sequence of past quakes in the order they happened. The cores from this coast reach back about 3,100 years, a long catalogue of disasters recorded in sediment. A normal turbidite has a particular shape. As the underwater avalanche settles, the heaviest material drops out first, so coarse sand gathers at the bottom of the layer. Finer, lighter silt drifts down more slowly and settles on top. The result is a layer that grades from coarse below to fine above, every time a reliable signature of a single settling event. Scientists can also date these layers. By measuring the steady decay of carbon in bits of organic material caught in the mud, they can estimate when each turbidite was laid down. Match the dated layers from one place against those from another, and the timing of past quakes across a whole region starts to come into focus. This is the toolkit that made the question answerable. By comparing turbidites from the area shaped by the northern fault with those from the area shaped by the southern one, scientists could line up their histories and look for moments when both faults seem to have fired close together. The layers near the junction, where both faults right into the same mud, were the place to look. And it was there, in that off-course core and others like it near Cape Mendocino, that the normal pattern broke. The layers came out backward, coarse material sitting above fine instead of below. That reversal is the clue at the centre of the whole investigation, and the next chapter reads it. The strange core showed a layer turned upside down. Where the normal pattern runs coarse at the bottom and fine on top, this one ran the other way, with coarse sandy material resting above finer silty sediment. That single reversal is the clue scientists call a doublet. The puzzle was how a layer could form backward when settling mud always sorts itself coarse first, fine last. The answer the team reached was that this was not one settling event at all. It was two, stacked so close together in time that they merged into a single odd-looking layer. Here is the reading they gave it. The lower, finer part of the layer formed first, the tail end of an avalanche set off by a great quake on the northern fault. Before that fine material had fully settled and sealed, a second quake struck, this one on the nearby California fault. The second shock launched its own avalanche, dropping fresh coarse sand on top of the still settling silt. The result was a layer with the order reversed, the signature of two quakes back to back. The name fits the find. A doublet is a pair, and that is what the layer records. A pair of great earthquakes from two different faults, separated by so little time that the seafloor could not tell them apart. The mud blurred them into one entry, because from its slow perspective, they happened almost at once. To test the idea, the team did not rely on a single core. They gathered more samples near the junction and dated them carefully, using the decay of carbon to fix the timing of each layer. The dates supported the reading. These reversed layers were not random accidents or ordinary aftershocks. They lined up as genuine pairs, two separate great ruptures falling close together in time. That distinction matters. An aftershock is a smaller quake on the same fault, an echo of the first. A doublet here is something else, two large quakes on two different faults, nearly simultaneous. The first is routine. The second is the rare and unsettling case, because it means the region's two giants can, on occasion, wake together. So a column of backward mud, pulled from an off-course patch of seabed, carried a large claim. It said the northern fault and the southern fault have sometimes ruptured almost in the same breath. The obvious next question is how often and when. The cores hold an answer, and the most recent case lands on a date already familiar from this report. The next chapter counts them. How many times have the two faults moved together? The cause near the junction suggests it is rare but real, and that the most recent case is one this report has already named. Reading the dated layers back through time, the researchers identified roughly 3 occasions within about the past 1500 years when the evidence points to paired ruptures, the northern fault and the southern fault firing within a very short span of each other. 3 events across 15 centuries is not common. It is the exception, not the rule, a pattern that surfaces only now and then in the long record. The most recent of those 3 is the Great Rupture of 1700, the same winter event dated by ghost forests and a Japanese logbook. The new work suggests that when the northern fault let go that night, the California fault to the south may have slipped close behind it, within minutes to hours. The orphan tsunami that crossed to Japan may have had a near twin that has gone largely unremarked until now. It is worth being precise about the strength of this claim. Pinpointing the exact gap between 2 ancient quakes is hard. The sediment can show that 2 events fell close together, but it cannot always say whether the gap was minutes, hours, or a little longer. The researchers themselves describe the timing as difficult to nail down. What the cores show clearly is closeness, not a stopwatch reading. Still, even a careful version of the finding is significant. 3 times in 1500 years, the record hints this coast may have faced not one great quake, but 2 in quick succession. The faults that scientists have long studied as separate systems may share a deeper link, an occasional tendency to set each other off. Why this happens is still an open question. One fault slipping sends out its own seismic waves and shifts the stress on nearby rock. It is plausible that a great rupture on one fault could nudge a neighbouring fault that was already near its breaking point, tipping it over the edge. The cores cannot prove the mechanism. They can only show the footprints the paired layers left behind. What the record offers, then, is a pattern and a caution. The pattern is rare paired ruptures, the last apparently in 1700. The caution is that the evidence is suggestive rather than certain, read from mud rather than measured directly. Both halves matter, and an honest account holds them together. This kind of paired event is not unique to the West Coast. The world offers one clear modern example, recorded by instruments rather than sediment, and it helps to weigh how seriously to take the idea. The next chapter brings it in. The idea of 2 great faults firing in close succession can sound far-fetched until you learn it has already happened in modern times, somewhere else on Earth, recorded by instruments rather than read from mud. The example comes from Sumatra, in Southeast Asia. In late 2004, a massive subduction quake struck off its coast, one of the largest ever recorded, and the tsunami it sent across the Indian Ocean became one of the deadliest disasters in living memory. That event alone reshaped how the world thought about ocean waves and warning systems. What is less widely known is what followed. A few months later, in early 2005, a second great quake struck a neighbouring stretch of the same fault system, just to the south of the first. It was a major earthquake in its own right, large enough to be a historic disaster on any ordinary day. The first rupture had loaded stress onto the adjacent section, and that section gave way not long after. The 2 Sumatra quakes were separated by about 3 months, not by minutes, so the match with the West Coast idea is not exact, but the principle is the same. One great rupture changed the conditions on a nearby part of the fault and helped bring on a second great rupture soon after. The faults talked to each other, and the conversation produced 2 disasters where planners might have expected one. This is why scientists take the paired quake idea seriously rather than dismissing it. Sumatra showed, in real time and with modern instruments, that great faults can trigger their neighbours. The West Coast cores suggest the same thing may happen here, sometimes on an even shorter timescale. The 2 lines of evidence, one modern and one ancient, point in a consistent direction. It is important not to overstate the comparison. Sumatra is a different coast, with its own fault geometry and its own history. The 3-month gap there does not mean the West Coast faults would behave the same way, and the ancient doublets here do not prove a Sumatra-style sequence is due. What the comparison offers is plausibility. It moves the paired quake idea from the realm of speculation toward the realm of things that genuinely occur. So the picture firms up. Ancient mud off Cape Mendocino hints at paired ruptures on the west coast. A real sequence in Sumatra shows that great faults can set each other off. Together they make a careful case that the region's two giants may, on rare occasions, move as one event spread across hundreds of miles. And there is a newer thread still, one that does not rely on old sediment at all. It comes from listening to the faintest quakes happening beneath Northern California right now. The next chapter follows it. The story so far rests on ancient mud and a distant example. A newer study from early this year adds a different kind of evidence, drawn not from the deep past but from the faint present. Beneath Northern California, near the same crowded junction where the great faults meet, the ground is never fully still. It produces a constant trickle of tiny earthquakes, far too small for any person to feel. Most are so faint they once went unnoticed even by scientists, lost in the background hum of a restless region. Modern instruments and computer methods have changed that. Researchers can now detect and sort these minute tremors in enormous numbers, picking out thousands of quakes that older networks would have missed. Each tiny quake is a pinprick of light marking where rock is moving, and together they sketch the hidden structure of the faults below. What that sketch revealed surprised the team. The earthquake zone beneath Northern California turned out to be more complex than expected, a tangle of faults and motion rather than a simple, clean boundary. The tiny quakes trace shapes underground that had not been clearly mapped before, showing a system with more moving parts than the older picture allowed. This matters for the timing question. A more complicated network of faults offers more ways for one structure to load stress onto another. If the crust beneath the junction is a dense web rather than a few separate strands, then the great faults that meet there have many small connections through which they might influence one another. The faint quakes are, in a sense, the region quietly showing its wiring. The study did not announce an imminent danger, and it is important to keep that straight. Tiny quakes happen constantly along active faults, and their presence is normal, not a countdown. What the work added was understanding, a clearer view of how intricate the ground really is beneath this stretch of coast. Clarity, not alarm, is the contribution. Read alongside the older evidence, though. The new study fits a consistent theme. The faults of the west coast are more connected and more complex than the older lone giant picture suggested. The doublets in the mud, the Sumatra sequence and the hidden web of tiny quakes all push in the same direction, toward a region whose faults are in conversation. That brings the report to the question people most want answered. If the two great faults did move together, what would it actually mean for the cities and coastlines in their reach? The next chapter walks through that scenario, plainly and without dramatics. If the two great faults did rupture close together, what would it mean? The honest answer is serious, and it is worth stating plainly without dramatics, because a clear picture serves people better than a frightening one. A great quake on the northern fault alone would already be a major disaster. It would shake the Pacific Northwest hard for minutes, damage buildings and roads across a wide area, and send a tsunami toward the coast. The region has planned for this single event for years, and the plans assume it will draw on the resources of the entire country to respond. The paired case changes the scale, not by making the shaking at any one spot worse, but by spreading the disaster across far more ground at once. The lead scientist put it in concrete terms. A rupture on both faults together could place several major cities into an emergency in the same compressed window, from the Pacific Northwest down into Northern California. He named the cities that would be in reach. The largest population centers of the region, spread along hundreds of miles of coast, could all be dealing with severe shaking, damage, and in coastal areas a tsunami at nearly the same time. Instead of one stricken region with the rest of the nation able to send help, several regions would be stricken together, each needing aid at once. The strain on response is the real difference. After a single disaster, neighbours send crews, supplies, and rescuers from outside the damaged zone. If the damaged zone stretches across multiple states and several cities simultaneously, that outside help is thinner, divided among more places that all need it now. The compressed timing is what makes the paired case harder than two separate disasters years apart. It is worth holding the scale steady here. This would not be the end of the region, or anything close to it. It would be a severe, demanding emergency across a wide area, the kind that tests preparation and recovery for years. Communities have come through great earthquakes before and rebuilt. The point is not ruin. The point is that the scope could be larger than the long-assumed single event, and this remains a scenario, not a forecast. The paired case is the harder possibility that the new science has brought into view, drawn from rare events in the deep past. It describes what could happen in an uncommon case, not what will happen, and certainly not what will happen soon. That distinction deserves its own clear statement, because it is easy to slide from could to will when the stakes feel high. The next chapter draws the line firmly, setting out what the evidence does not say. It is easy to let a scenario harden into a prediction in the mind, so this chapter draws the line firmly. Here is what the evidence does not say. It does not say a paired rupture is coming soon. The doublets in the mud show that such events have happened perhaps 3 times in 1500 years. That is rare by any measure. A rare pattern in the deep past is not a signal about the near future, and nothing in the cause points to a date. It does not say the two faults always move together. Most great quakes on these faults through the long record appear to have happened alone. The paired case is the exception that surfaces occasionally, not the normal way the faults behave. The lone great quake remains the more common outcome. It does not say the small cluster that afternoon was a warning. Those 3 quakes sat on a sliding fault in the open ocean, the kind that shakes often and harms little. They carried no message about the great faults and no hint of paired ruptures. They shared a calendar day with this larger story, nothing more. It does not say anyone can predict the next great quake. No method exists to name the time or place of a future earthquake, on any fault, anywhere. Probabilities describe the long run across decades. They cannot tell a person whether the ground will move tomorrow or in 50 years. The new timing research does not change that limit at all, and it does not say the science is settled. The paired quake idea rests on reading ancient sediment, which is careful work but indirect. The exact timing of the old events is hard to fix. Other scientists will test the claim, look for the same patterns elsewhere, and either strengthen it or push back. This is a live area of study, not a closed verdict. What the evidence does say is narrower and steadier. The West Coast faults are more connected than the old lone giant picture assumed. On rare occasions in the past, 2 great faults appear to have ruptured close together. That possibility is now part of how scientists think about the region's risk, and it raises the upper edge of how large a future disaster could be. Holding both sides keeps the picture honest. The risk is real and worth respecting. The timing is uncertain and cannot be forced into a date. Neither half cancels the other. They simply describe a serious, uncertain hazard, which is what this coast has always lived with. Living with that hazard wisely does not require fear. It requires a few plain settled habits that hold up whether a quake comes from the sliding fault offshore or one of the giants beneath the sea. The next chapter sets them out. Living on this coast does not call for fear. It calls for a few plain habits, the same ones whether the next quake comes from the sliding fault offshore or one of the great faults beneath the sea. None of them are complicated, and all of them are worth setting in place before the ground ever moves. Start with the motion itself. When strong shaking begins, the standard guidance is simple and well tested. Drop to the floor, take cover under something sturdy like a solid table, and hold on until the shaking stops. The aim is to protect yourself from falling objects, which cause most injuries in a quake. Trying to run during heavy shaking usually does more harm than staying low and covered. For people on the coast, there is a second rule that follows the first. If the shaking is strong or lasts a long time, do not wait for an official warning before moving to high ground. With the nearest fault so close offshore, a tsunami could arrive within minutes, faster than any alert system could reach everyone. The long shaking is itself the warning. Move inland and uphill, on foot if roads are blocked, and stay there until officials say it is safe. Preparation at home is the next layer. Emergency planners in this region suggest keeping enough food, water and basic supplies to last about 2 weeks, longer than the usual advice elsewhere. A great quake could cut roads, water and power across a wide area for an extended time, and outside help may be stretched, especially in the paired case described earlier. 2 weeks of self-sufficiency is a realistic cushion. Technology adds a thin margin of warning. The region now has an early warning system that detects a quake the instant it begins and sends an alert to phones and devices in the seconds before the shaking arrives. Those seconds are short, but they are enough to drop and cover, to step back from a hazard, or to stop a vehicle. The system cannot predict a quake, only sense one already underway and outrun its slower waves with a fast signal. A few small steps around the home round it out. Secure tall furniture and water heaters to the wall so they do not topple. Know how to shut off the gas and water. Pick a place for family members to reconnect if separated. These are quiet, one-time chores, and they pay off precisely when everything else is chaotic. None of this assumes disaster is near. It assumes only that the coast sits on active ground, which it does and always has. Preparation is not a prediction. It is the calm acceptance of a place's nature, the same way people in storm country keep a plan for storms. The habits sit in the background and ask nothing until the day they are needed. With those habits in place, the broader story can rest where it belongs, as something to understand rather than dread. The final chapter returns to the quiet afternoon where this began, and to what is worth watching from here. Return to that afternoon off southern Oregon. The seafloor slipped about 95 miles offshore. A magnitude 5.7 rolled out through deep water, and a few dozen people felt a gentle sway. No one was hurt. No wave formed. By evening it was a small note in the day's news, the strongest of 3 modest quakes along the coast. What is known about that event is settled and calm. It struck on a sliding fault in the open ocean, the kind that shakes often and threatens little. Its sideways motion could not raise a tsunami. Its distance offshore softened it to a tremor by the time it reached land. On its own terms, it was an ordinary day in the life of a restless coast. What is known about the larger picture is steady too. The Great Fault off the Pacific Northwest carries a real chance of a major quake within the lifetimes of people living now, somewhere in the range the studies describe, with smaller partial ruptures more likely than the largest full one. That risk is long-standing, well-studied, and worth respecting without dread. What is newer, and still being worked out, is the question of timing. Evidence read from seafloor mud suggests that on rare occasions, perhaps 3 times in 1500 years, the Northern Fault and the California Fault to the south have ruptured close together, the most recent apparently in the winter of 1700. A modern sequence in Sumatra shows such pairings are possible. A study of tiny quakes beneath Northern California shows the ground there is more connected than once thought. What remains uncertain is just as important. No one can predict when the next great quake will come, or whether it would arrive alone or paired. The timing of the ancient events is hard to fix. The paired quake idea is suggestive, not proven, and other scientists will test it in the years ahead. The honest state of the science is a serious possibility held with open hands. The thing to watch from here is not the next small cluster. Quakes like the 3 that day will keep happening, and they carry no special message. The thing to watch is the research itself, as scientists gather more cores, refine the old dates, and either strengthen the paired quake picture or revise it. That is where the real understanding will grow, slowly and carefully, the way it always has. For now, the coast goes on as it always has, beautiful and active, carrying a risk that is real but not urgent. The wisest response is the calm one. Understand the ground you live on. Keep a few simple plans in place, and let the small quakes be what they are, the ordinary breathing of a living edge of the continent. That afternoon off Oregon will fade from memory soon enough. The questions it brushed against will not. We will keep watching them, calmly and closely, and return with the next report when there is something steady and true to share.